We've seen how dipolar forces are expected to raise the boiling point of a material. But what's going on with nonpolar molecules? Why would those molecules come together? And what effect does the mass of a molecule have on the boiling point? Let's think harder about these questions. Previously, we looked at this boiling point data and found that when molar masses are similar, polar materials tend to have higher boiling points than nonpolar materials. HCl has a higher boiling point than F2. ICl has a higher boiling point than Br2. But there is a second way to look at this data. What if, instead of looking across, we look up and down? The observation is that when comparing nonpolar materials, the heavier Br2 has a higher boiling point. When comparing the polar materials, when H is replaced by the heavier I, the boiling point is higher. In each case, when comparing two similar materials, the lighter material is lower boiling, whereas the heavier material is higher boiling. We see this again in a figure from our textbook. The boiling points of the noble gases, shown by the yellow points connected by the black line, show an increase in boiling point with an increase in mass. Same with the halogens, shown by the blue points connected by the red line. In each case, when comparing a closely related series of materials, such as the monoatomic noble gases or the diatomic halogens, as the molar mass goes up, the boiling point goes up. But wait a minute. The materials in the figure are all nonpolar, so why would the molecules want to attract each other, and why would the mass make a difference? What forces are present here in the nonpolar materials? To understand this, let's consider two nonpolar molecules next to each other. We need to recognize that nonpolar molecules are nonpolar on average, but electrons are free to move around in their orbitals, and molecules may, temporarily, have more electron density at one end. This can lead to what we call a temporary dipole. Let's say the molecule on the right temporarily has more electron density at its right end, making that end partial negative and the other end partial positive. This temporary electron distribution can affect electrons in neighboring molecules. Imagine that you're an electron in the left-hand molecule and you see a partial positive charge next to you. You are going to want to move toward that positive charge. We say that this forms an induced dipole in the left-hand molecule in which there's a partial negative charge on the right. Notice that we now have an attraction between a temporary partial positive and negative charge. This is what we call a dispersion force. It's sometimes called a van der Waals force or a London force. Regardless of the name, it gives a basis for these formally nonpolar molecules to attract one another. Why does mass matter? We know from the kinetic molecular theory that heavier molecules move more slowly in the gas phase, so there is more time for this type of interaction to occur when molecules come together. While electrons make up very little of the mass of a molecule, heavier molecules will have more electrons, so the partial charges that result can be more significant. We say that heavier molecules tend to be more polarizable. They have a greater polarizability, which is a measurable quantity. This all means that the dispersion forces will be greater in larger molecules, which results in the higher boiling points that we observe.